Alright guys, welcome back to Introduction to Computer Networks. This is Polly again, streaming live from NTU. And good morning to Yanjia, Hanzhen, and Yuanhao. Alright. And you know what guys, there's nothing special in the announcement, so we'll go ahead and jump into the topics today. Okay. So the topics today are really exciting. We have only 4, and all of them are about IP addresses. Recall quiz 35, right? You guys were working on, how to write the ABCD/X out of a network mask or the network part of an IP address. Today, we'll continue to talk about IP addresses. It's a very fun topic, okay? And so consider, let's break the 4 topics into 2 parts. The first 2 topics are more about assigning the IP addresses, how the IP address is entirely assigned to a network, and how the network assigns an IP address to an individual machine's network interface. Okay? Yeah, and hi, Qing-Ying, Matthew, and Yujie. Good, you guys are just in time. So, first topic is called DHCP. It's about how a network assigns an IP address to a particular machine. Okay? In this first video, you will hear, in the first part, there are 2 ways, okay, in general. So there's no one single way. And one is manual, the other is dynamic and automatic. DHCP is a protocol that allows you to do dynamic and automatic IP assignment. All right. Now, in the second part, you will hear a very high-level overview of DHCP. And pay attention, there's a keyword called lease. In a way, when you get an IP address from DHCP, you are not really owning the IP address. You are more like renting an IP address for a period of time. Let's talk about how a host gets an IP address. There are 2 ways, especially in the older time. You have to talk to the system admin first. System admin is going to give you the IP address. And then you manually type up the IP address at the specific place in an operating system. Now, how you do that can change from operating system to operating system. Where you do it exactly could also vary within the operating system from version to version. And some of you might need to reboot, okay, the machine as well in order to have the IP address taking effect. So this process here, the manual approach, very tedious, out of fashion. More fashionable today is to run DHCP, the Dynamic Host Configuration Protocol. What it does is to get the host and IP address automatically and configure it automatically. The service is entirely plug and play, so there's no manual effort required. Really nice. And we're using it every day. This DHCP protocol is already part of the protocol stack and part of the operating system, part of all the operating systems these days, including the mobile phone operating system. So formally, let me introduce DHCP. It allows us to acquire IP addresses dynamically. So what happened there is that our side of DHCP is running the client process. The subnet you'll be joining. Okay? The server process is running on the subnet, running on one machine on the subnet. So the 2 sides, client server, will negotiate and reach an agreement. So that agreement is actually a lease on a specific IP address. And that's why my host here gets to use a specific IP address. So with this, we bypass needing to communicate with the system admin, a real person. And the assignment is also automatically done because it's all part of the operating system. But essentially, okay, after the negotiation, we get to use an IP address. But as you see here, it's a lease, meaning the IP address is also temporarily allocated. So that is why it's called the dynamic host configuration process. It only runs for a while. If you leave the subnet, this IP address will be reclaimed by the server. But don't worry, as long as you stay in the subnet, stay connected, stay on, then you get to reuse the IP address. Okay? And this is done by exchanging messages again between the client and server. So there are some more messages being exchanged and periodically so that we could renew the initial lease. Okay, so that is generally how the DHCP works. You see, this is really, really nice for us in living now a very mobile lifestyle. Okay. And the process is very simple. This negotiation process is very simple. A very simple four-way message exchange. Okay. And an even simpler version is just two-way exchange. Okay. So these two first messages, they can be actually bypassed if the user is coming in and out really fast. Typically, the OS on a smartphone implements more this version of DHCP. Now, let's take a look at the scenario and go through these four messages in a bit more detail. So here it is. We've used this network already earlier to explain, right, what's IP address format and what is the subnet address. So let's assume we set up a DHCP server here connecting to 223.1.2 subnet. And we carrying a laptop, okay, running an operating system with the client process already running. So the arriving client process here, server process here. All right, now next video, Polly is going to give you the a detail of the four-way exchange, including the two messages that are optional. You will see what's inside, okay, each of the messages. The first message, DHCP discovery. What it does is the client asking, in a broadcast way, yeah, is any of you guys the DHCP server? So if we look into the packet, you should see the source looking like this, a null IP address. And the DHCP client is default on port 68. The server, on the other hand, on port 67. Destination will be going to the DHCP server. But hey, the client doesn't know if there is a DHCP server in the first place, not to mention the exact IP address. So we're sending it to here, the broadcast IP address. A message carrying such an IP address is going to be received by all hosts on the subnet. Therefore, DHCP server being one of the hosts on the subnet will definitely receive the discover message. Why I address here? Yeah, this is the field to store. The IP address potentially will be assigned to the client. Now, the client has no clue, therefore, it's null. Last is the transaction ID. Now, this is actually quite critical. Usually, it looks like a random number. Okay? Different clients will actually send discover messages carrying different transaction ID. Now, these IDs are also to tell the arriving clients apart. So there could be other clients arriving as well. And they could be sending these DHCP discover messages about the same time. Servers sending responses, DHCP offers, okay, about the same time. How does this guy know which offer is for this guy, and how does this other guy knows, right, which offer is for him? So transaction ID, okay, typically different, coming from different clients to enable the clients to tell whether the reply is coming for the host or not. So very important. And to respond to the discover message, the server sends the offer message. Okay, so this is saying, yeah, I'm here. And here's an IP address you could use. And inside the offer message, you see the source being the server's IP address. Destination, again, the broadcast address, because arriving client doesn't have an IP yet, but will still receive a message going to the broadcast IP address because everyone on the subnet will receive such a message. And we see here, the server is offering this IP address to the client. Transaction ID, yep, the same pair. Okay, so this offer is for this discover message. And you see, server here, while offering a specific IP, is also saying, hey, client, you get to use this IP address for 3,600 seconds long. Okay, so it's the duration of the lease. Client then say, yeah, DHCP request, okay, I'm going to take the IP address, and this is the content, asking for this IP address. And it's a new transaction for the song. In return, the server sends back ACK, okay, which is simply saying, okay, you got it. Okay, therefore, you see, you got the IP address for this song. And this, again, corresponds to this, okay, not to be confused with other clients requesting for other IP addresses. So this is the exchange of the four-way messages, okay, in DHCP service. Now, in the exchange, DHCP server actually say more, okay, not just the IP address, but a whole bunch of other things that are very critical setting up, okay, the subnet on the hosts. So first is who the first hop router is, because the host message is going out onto the subnet. The default next hop is always the first hop router, because the first hop router then, after picking up, then can determine where else to forward it further. Another important information, DNS servers. This is very critical, right? Because you are requesting www.google.com or www.something, okay, by the name of the server. Okay? In order to know the IP address, you also need to configure on your host the DNS servers. I know some of you might have some DNS server IPs assigned already, configured already, but if you connect to DHCP server is going to also add some IP addresses into that part of the operating system. Okay, so the name and the IP addresses of some DNS servers by default. And then the network mask. So this is to tell the host how long is the subnet part of the IP address. So provided the IP address, the DHCP server is also saying that, hey, what is the subnet part? And therefore, the client also know what is the host part.
All right, so DHCP allows the network to assign the IP address. It also assigns the first hop router, the network mask. These are important for routing purpose. And then what? The DNS server's IP address, because when users are actually browsing the web or connecting to other computers, we get the names. Okay. First thing to do before one can use forwarding routing function yet is to translate from the names to the IP address. So these three other pieces of information are also very important to have at the bootstrap phase. Okay, so DHCP essentially is a protocol to allow us to bootstrap and start connecting to the internet. All right. Yeah, hi. I think to Zhu Xun, Lucas, Yu Ting, Eneko, and Minghua. Last video about DHCP is this. Okay, I'm going to show you exactly how DHCP messages you see earlier, right? There are 4 messages. For some scenarios, you probably just exchange 2 of the 4 messages. But whatever messages you will be exchanging will be going through the protocol stack to the DHCP server and back. Okay, so these messages, guys, are actually originated from the application layer. So we now know network IP addresses is a network layer notion. DHCP, we talk about it in chapter 4, but the fact is that DHCP is implemented in the application layer. Okay, and these DHCP messages are sent over a UDP connection. Guys, does this sound familiar? Do you recall that in chapter 2 we talk about a protocol that is also functioning in a way that one can discover the IP addresses of a machine, isn't it? And that is implemented in the application layer, and the messages are being sent through a UDP connection. Aha. Think about this. If you recall what that protocol is, that is implemented in the application layer, send messages through UDP connection that also handle IP addresses. Type it up on the chat as Polly plays this video. So this is the exactly how DHCP messages will go through the Internet Protocol stack to the DHCP server and back. And towards the end of the video, you will also see the exact DHCP requests and ACK messages.
And to illustrate, you see in this DHCP example, host is right here. Okay, we just joined. And DHCP server is already up, and it happens to be running on the first hop router. So what happened there is, the connecting laptop is going to send a DHCP request message out to the network. So this is the simplified version of DHCP. Sending request and server sending ACK. So the laptop here is asking for its IP address. In addition to that, first hop router, DHCP server, and Dynamics. So DHCP is actually right here, an application layer protocol. And that DHCP discover or DHCP request message is going to be what? Passed to the UDP and adding the UDP header, push down to the network layer and adding the IP header, and push down to the Ethernet and adding the Ethernet header and trailer. So the DHCP request gets encapsulated into an UDP packet, further into an IP packet, further into an Ethernet frame. So DHCP is actually implemented at the application layer. Just like DNS, seemingly a lower level functionality, a general functionality, for everyone on the internet, but implemented at the application layer. Complexity at the edge. and it's using UDP as the underlying transport layer service. Now this frame, carrying destination address being broadcast 255.255 all the way, is going to reach all the hosts on the subnet. So this is the entire subnet. By the way, this is an Ethernet switch. It's a rectangle, not quite a circle, so this is not the router. Okay, so yeah, this is actually the link. Okay, so this interface and this interface are connected through this link. So every host on the subnet is going to receive the DHCP discover message. So therefore, the server here is going to pick it up. So this is what going to be extracted, okay, and passed up to the IP layer. This extracted, passed up to the UDP, and this extracted, and eventually reaching the application layer. So the server then can see, this is a request message, therefore send back a reply. So you see here, going all the way, Ethernet gets demuxed to IP, to UDP, and finally, server side of DHCP. Now, the server then will generate the ACK message containing the IP address of the first hop and the IP addresses of the DNS servers, and so on and so forth. So, process is very similar, encapsulate to UDP, encapsulate to IP, Ethernet, and destination address being broadcasted. Yeah, the host here, although not having a specific IP address, is going to pick it up. Okay, so client now knows the IP address of itself, name and IP address of the DNS server, and the first hop, as well as what? The network mask. So what I'm showing here is the result of sniffing DHCP messages. This is a DHCP request message, and this is a reply of that. Earlier we actually called it the ACK packet, okay, ACK message. And I can use tools like Wireshark or TCP dump to sniff packets travel the internet. Now, after sniffing, you're gonna see the content inside the packet. So what I'm showing here is, this is the request message. So you see boot request, and in the reply or in the ACK message, you see it says boot reply, and you see transaction ID, transaction ID, and they're identical. So this ACK here is for this request. And then you see also specifically the client not having an IP address, but it still have a MAC address. So that MAC address is actually hard-coded into the network interface card that came with your machine. Okay, so that is already existing. And that is something that the DHCP client is going to send to the server. So server can identify you somewhat by the MAC address. And then, this is DHCP request, okay, and this is DHCP ACK. And the client is asking for these, right? So the IP address, okay, so IP address is not clear yet, so requesting, this IP address. Okay, so this is not a sure thing. It's just that the client suggesting, can I get this IP address? And it's also asking for domain name servers, and the subnet mask. Server here, in the response, it will see, okay, hey, client, okay, it's okay to use this IP address. Go ahead. In the meantime, it's returning also the subnet mask, the first hop router, as well as the IP addresses of the DNS servers and the domain name. So
so let me just cut a few seconds off that because you see the message details. And we do need a little bit more time today. Okay, good. So before we go into quiz 36, I hope that you see more clearly that DHCP, how it works, and a bunch of information that are very important. IP address, of course. The first hop IP address, the network mask, and the DNS server's IP address. Okay, so keep these in mind. And now let's move on to quiz 36. So quiz 36 is an open-ended quiz, so you can probably see already. Let's go to the whiteboard mode. All right, good. So this news Polly has extracted off the web actually says this: don't expect high of the free Wi-Fi networks in Taiwan. Okay, sorry guys. Okay, so hey, I don't know if you have used the Taipei free Wi-Fi. It is free, but people complain very often that it's useless. Okay, and I wouldn't say that this is a complaint only to Taipei free. I think in many of the free Wi-Fi services you try to connect to, it's very often that you have trouble using it. Okay, so maybe what I can do is to translate the news. Okay, so let's look at this. Translated is this. There are quite a few of these free Wi-Fi access points around. Okay, and there are friendly gestures to the travelers in general. But 40% of the users are not satisfied with these services. Okay? Among the users who are not satisfied, most of the users complain about this. Hey, I can't even connect at all. Okay? Now, some of you might have experience using the free services and find that the transmission rate is low, the speed is low, and the signal is weak. But the mass majority of complaint is this: I can't even connect. Q1 ask, okay, what do you think is the problem? You tried to connect to a free Wi-Fi service, but you couldn't. Second, if you guys come up with the reason why, how do you address that problem? Okay, good. So this one is a little bit challenging. Okay, gather your teammates. Let's go to the score space. This is channel week 12, quiz 36. Guys, gather your teammates. You have 8 minutes to discuss and 1 minute to type up your opinion and solution. Okay, let's start counting time. Okay, you don't need 8 minutes, I see. Okay, too many people using Wi-Fi at the same time. And why would too many people using Wi-Fi at the same time then prevent you from connecting to it? Okay, increase the number of points or the capacity of each point. So what do you mean by points? Do you mean AP, the access points? I guess so, right, Eneko? And the capacity in terms of what? Bandwidth or what? Okay, so the issue at hand is that you can't even connect, not even think about sending data at all. So what is the capacity that's not enough to serve so many people? What is the resource that's lacking so that when there are too many people around, we couldn't connect? Okay, so team 17. All right. Yeah, I know it's a little fuzzy, but I think it's okay. I'll accept the solution you guys have. Ah, Lucas, team 2. So I guess team 2 is saying this: if the IP address is too small, for example, only 2 to the power of 8 bits, 2 to the power of 8, if only 8 bits is the host part of the network address, then you can only accommodate 2 to the power of 8 machines. And that is how many hosts? I think that's 256, right? Or 512. I think it's 256. So 256, in case you have a crowd more than 256 coming in, then some of these guys will not be able to connect. So in a way, team 17 is also correct. You kind of need to have two conditions, right? Too many people, too few IP addresses. And then you have this issue. Not being able to connect. So I guess team 2 and team 17 are actually forming a team to provide a complete solution, complete answer. And team 2 says, yeah, so you guys learned about the structure of the IP address, isn't it? So if you want to make sure that there are more free IP addresses are usable, okay, then oh wow, okay, suddenly, guys, very good. So one way to increase the space of free IP addresses usable is to reduce the subnet part of the address length. Yeah. So if the host part is only 8 bits, maybe extend it to 10 bits, right? Then you can now accommodate 1024 users. Deploy more APs. Well, deploying more APs is a little bit tricky. In case each AP is allocated a different subnet space, then it will help. If these APs are sharing the address space, then this is probably not going to help much, guys. One can actually build a subnet, creating multiple access points for the subnet. Okay, you will see that at any area. At any point in the area, the signal strength will be high because you have multiple APs. But that doesn't prevent the issue of having too few IP addresses to assign. Okay, so this issue that people have trouble even connect to the network, in case it's because of IP address shortage, deploying more APs don't necessarily help. Thank you, Lucas. So Team 2, Team 17 nicely complement each other. Okay, let's see. Team 1. I would rather say this is a systemic issue. Oh, okay. Oh, wow. Law prohibits foreign investment in this industry. Oh wow, lack of competition. There's no sufficient competition. Even worse, the dominant player, CHT, the Zhonghua Telecom, okay, is still, much owned by the government. Libertarian, I strongly dislike this, okay. Yes, you are entitled to think so. Okay, and Zhonghua Telecom deliberately prefers using routes with higher latency to force content providers paying extra bucks for local connectivities. You know what? That is a little bit sad, but true. Okay, August, you're insightful. I know nowadays many of the ISPs compete in an unfair way. Because inside internet, particularly when you own an AS, where the AS is a key hub of connectivity, that AS can play a bully sometimes. Okay, and of course, among tons of other issues. Very interesting solution. Very interesting observation from August, from Team 1. And how do you address this issue then? We're gonna address this. We open the telco industry to everyone except. Okay. So you understand the tension here across the straits. Yeah, I guess what you're trying to say is that to open up a little bit to allow some level of competitions. Okay. Interesting. So you think this is more a, hey. If Lucas is right, then Zhonghua Telecom or the companies offering these free Wi-Fi services, in case, these people are taking these seriously, they should be able to discover, hey, obviously the address space is not enough, and try to fix it. And it's not being fixed. Then it's probably something to do with the operator, how the operation team is managed. Very interesting. let's see, team 4. Insufficient access points. Too many people try to connect to the Wi-Fi, but there's too few access points. So more access points, adequate coverage. So you see, adding access points definitely expand the space, where you expand the signal strength and expand the space of access. So in case you find the problem is that there's not enough access points, then you add access point, makes sense. Okay, but too many people trying to access does not necessarily get addressed by just adding access points, because some of these guys might have trouble getting the IP addresses in the first place. Team 15. There are too many requests for a limited number. Okay. Spend more money to okay. Increase the number of hosts. Obviously. So team 15 nicely aggregated team 2 and team 17's solutions or observations. Okay. So team 4, think about it. Okay. I think you were probably thinking that it's a bigger crowd and therefore it expands a bigger space, and therefore having more access points makes sense because the coverage is bigger. Okay. Team 7 might assign same IP to multiple devices. Yeah. This, you know what, could happen. Allocate more IP addresses, shorten the lifetime for the connection. So when a DH server is misconfigured, this could happen. Yeah, so again, operation issues. Allocating more IP addresses, yes. Oh, cool. Team 7, Boyun, you guys are good. Hey, in the first video, I asked you guys to pay attention. There's a keyword. What was that? Lease. When an IP address is assigned by a DHCP server, you are allowed to use this IP address for amount of time. So shorten the lease time. Okay, would also allow a faster recycling of the IP addresses, because in a for example Taipei free or Taipei Metro free. So these are usually the spaces for people, travelers, moving around. So they come and go. So if we assign these IP addresses and with a long lease, right? And the people getting the lease quickly move away, then it's a waste of resource, isn't it? Cool idea, very observant. Okay, nice insight. Team 7. Team 10. It can sometimes be too far. Yeah, I think Team 10 here, you are going in the direction of Team 4, right? Having more people, meaning people kind of span a wider area, and you can potentially be far away from the AP. Okay, so and the problem is probably more serious, right? If we are moving around, we might connect or might not connect depending on whether we are moving away from the AP or not, isn't it? Introduce more hotspots. Yeah, so introduce more APs. That would ensure the coverage is wider. All right. Another answer from Team 1, UG. It's okay to keep your answer. To the number of IP address you can assign. Expanding subnet or use IPv6. Okay, we have not yet talked about this. Okay, we'll talk about this the second half of today's lecture. Yeah, so IPv6 is the next version of IPv4. So currently in IPv4, we use 2 to the power of 32 bits, okay? That much IP addresses as the address space. In IPv6, we'll go from 32 bits to 128 bits. Wow, that's a lot more IP addresses we can allocate. Yeah, so this can definitely address the issue, okay, of IP address shortage. Several reasons. Team 5, very good. Interference, distance from the routers, or being overloaded, router misfunction, bandwidth limitation, too much, try to connect at the same time. Wow, okay, many different causes. Check signal strengths, restart router, reduce interference. All right, okay, very good, very complete, okay, diagnosis. Cheng-En here, let's see. Too many users are connected to the same access point simultaneously. Okay, congestion. Slowing the speed for everyone. Okay. So slowing speed is actually the second highest complaint. Okay. 74 complain that we couldn't connect, and 60-ish people complain the connection speed. Okay, so yes, this is indeed the complaint for the second one. And too many trying to use the bandwidth, share the bandwidth, therefore it's slower. Network B? Okay, I guess Team 9, you guys have different opinions between the members, I see. Okay, yeah, another member says that there's not enough IP address. So having not enough IP addresses, for sure that some will not get connected at all. Excess use of mobile device in the public. Decreasing network efficiency. Access point is also not enough for the number of users. Okay. Install more access points. Purchase personal wireless network yourself. Yeah, sure. Switch to 4G, 5G. Okay, very effective solution, I have to say. Okay. But this statement is also saying that, hey, Taipei free is free, but pretty much useless, right? Because you can use it anyway. Too many people want to connect at the same time. Possibly the switch, yes. Yeah, the AP might fail to send the request to DHCP server. That's possible. Yeah, so the bandwidth issues might be at the AP side. Okay. The host part of the IP address, yeah, too short. Again, and assorted, okay, cause of the problem. Extend the number of bits for the host part. Examine the function of the switch. Too many people try to connect at the same time. Signal poor, okay. Set up more APs, maybe showing the current capacity. Interesting. Do you mean like showing the current capacity to the users who try to connect? Interesting. This will be really useful feedback. Okay, Yuting, Team 4, you are very good. Very business-oriented thinking. So at least the users know, right, whether they stick and try again. If it's too crowded, maybe just switch to personal wireless network. Because keep trying is something that frustrates people, isn't it? Team 11, devices set for static IP only. Okay, maybe your device is set to use static IP. Of course, then if you go to a different subnet, couldn't connect. Too far away from the AP, or maybe the network of interesting. Yeah, so I guess you meant that if you're configuring a fixed IP and you move to another, and so then you need to reconfigure your device so that it will dynamically use DHCP to connect, right? Interesting point. So maybe the user couldn't connect it at all is because the user's own setting, okay, on the phone or on the laptop. Too far away from the AP. Changing the setting. Get closer. Teammate, not enough number of IP addresses, too many people. Increasing the IP address, definitely. Encouraging people. Okay, yeah. So if you have like all you can use cellular data access, then yeah, encourage them to switch to cellular data plan. Connect to a private Wi-Fi instead of the free Wi-Fi. Okay, sure. This way we will offload to other networks instead of all of us using the free Wi-Fi. Okay, good. Yeah, so we see more and more ideas coming, right? After you see others' ideas. Okay. Again, these open-ended quizzes are more for us to brainstorm. Okay, so you can see the thinking process. Okay, you can see people approaching the issue. This is a real problem, right? I'm sure that Taipei Free, okay, will need to address the problem. But if they hire the class here, they will get to know more what might be the causes, and they can go ahead and check and see if they can improve their service. Okay, so this is exactly the design process. Or for a system that's already operating, the redesign process, the iteration process. All right, great. So with the discussion, I think you know very well how DHCP works and how it's everywhere pretty much nowadays in our daily life. Okay, when you go to the public space and try to access Taipei Free or something free, first thing your client does is to send DHCP discover, okay, or maybe just DHCP request. All right. Now let's move on to the next topic: hierarchical routing. All right. DHCP is about how a network assigns an IP address to an individual machine. This topic is about, hey, how the network get a block of IP addresses at the first place.
So that was how a host gets an IP address. We ask the system admin for one or DHCP server for one, which is configured by the system admin. So the bottom line is, how does the system admin get a block of IP addresses so that the system admin can assign to individual hosts? So the next question we're asking is exactly that. Yeah, how a subnet gets the subnet part of the IP address? The answer is quite straightforward. As we ask the system admin for one, system admin asks the higher level system admin for a block of IP addresses. So if we are customers of an ISP, we ask the ISP for the address block. So what I'm showing here is an example. ISP owning a big block of IP addresses. Okay, so by big block, this is how big a block is. Now the prefix of the subnet address of the ISP is only 20 bits, so only up to here. Therefore, that allows us a bigger free IP address space. Now, if there are 8 customers, okay, subscribing from the ISP, organization 0 all the way to 7, ISP can further divide the bigger address space this way, extending the prefix by 3 bits. So that is pushing it further here. So 3 more bits being included into the subnet ID. Because there are 3 bits, so we could uniquely separate the 8 different organizations. But as a result, we get what? Less free IP space. Each now gets only this much. That is what? 1/8 of the original space. So we are splitting the IP address to 8 equal ways. And it is done very easy by just simply saying this, extending from 20 to 23. Let's say if organization 7 here having 4 departments and each ask for equal share, then very straightforward, right? Extend from 23 to 25, the prefix lengths. And so we'll be actually doing, something like this. Take 2 more bits here, and there are 2 bits, therefore we could identify 4 departments uniquely. And the IP address space is now down to 2 to the power of 7, okay? 1/4 of the second level organization here. So you see, using the prefix there, by sliding it to the right, we actually create also a natural hierarchy in the IP address space and dividing the IP address space. Just like how human beings divide and organize bigger society to smaller society and even smaller society. So this type of addressing, the IP addressing, is also called the hierarchical addressing. Okay. There's actually one more benefit of it, not just that dividing the address space is made very easy, but also this. We could do very efficient route advertisements. Now, routing is one of the major functionality in the network layer. We have not yet talked about it, so in order to explain how efficient this is, let me just give you a slight overview of routing.
And of course, the next video is the slide overview of routing.
The goal of routing is to form these forwarding tables, if you recall, right? Destination IP and outgoing interface. Now, the way these entries are formed is this. If this is a destination, if somebody else on the internet wants to send data to this guy will need to announce its IP address, okay, in an advertisement and travel through the network like this to outside. That is how the router here discovered, oh, okay, I see a destination potentially this way. So that IP here, and the outgoing interface is this guy here. Now for a guy, okay, who's connected to the internet this way, that advertisement will go down, this other interface. So this other guy here, IP prime, the output interface will be linked here. So that is the general idea of routing. But then you see, for each machine here having an IP address, in order to allow other people sending packets to it, they would each need to send an advertisement announcing its IP address. Okay? And there are these many different IP addresses possible, so potentially worst case, right? Lots of advertisements each of these organizations need to send and travel on these links. And you know what? The most scary thing is this. All these need to go out to the internet, so the ISP needs to send these many advertisements. And that is just not going to scale. Okay, that will be a lot of bandwidth consumption just to send the advertisements. The solution is actually related to the forwarding mechanism in the router. If you recall, instead of listing individual destination IP here, rather we do this individual prefix, okay, and then outgoing interface. So when a packet arrives, the destination IP address matching the prefix, then we send it out on the outgoing interface. You know what? Isn't this a prefix? Isn't this a prefix? So what we're doing, in fact, in the internet is not to send individual IP address in the advertisement. We send an individual prefix in the advertisement. So what's happening there is a prefix in the advertisement gets here. Router here, receiving it, pass it down further. Router here, receiving it, pass it down further, but also add the entry prefix here. And because it's coming this way, so this OIF is going to point to this interface. So when a packet arrives here, matching the prefix, go on this interface, and coming here, this router is going to forward it similarly down this way, and then coming into the organization 0. So by announcing or advertising the prefix, okay, we also draw the data into the organization. And the data is actually destined for one of the hosts in the subnet anyway. So the routers inside the subnet there, we just, we'll be doing further routing there to get to the final destination. Nice. So you see, instead, organization 0, 1, 2, all the way to 7 will be sending one advertisements only instead of these many advertisements. What's even nicer is this, the ISP. ISP doesn't need to send 8 individual advertisements out, just send one. Because it's very easy to aggregate all these, right? Because this is the coarser granularity covering, right? Superset of all these subnets prefix. So there's just one advertisement out this way. One on the link, one on this link, one on this link. advertisements, the distribution of it, very, very efficient. And so here, the entry is simply 200 something something 6.0, and it goes on this interface. Data matching this will all fit and then go on here. This router here then will split the packet 8 ways, and by checking the destination address of the packet to these 8 different prefixes and see which prefix matched better. So that is the idea, and why we say more bandwidth here. This is the third benefit of doing the prefix matching, in addition to what? Making the forwarding table smaller and the lookup process faster.
All right, nice, isn't it, the IP address? It's easy to distribute, as you see in the previous video, from bigger organization to sub-organizations to sub-sub-organization. And in terms of routing, it also helps aggregating individual advertisements from sub-subnet to subnet to network. Easy distribution and aggregation. So internet routing, internet addresses is hierarchical. Okay, so hierarchical addressing helps hierarchical routing. And guys, it's now 11:11, a perfect time to take a break. Okay, we'll take a 10 minutes break and resume at 11:21. right, welcome back. It's now 11:21. Okay. Yeah, so guys, sorry for the discussion between August and me. Yeah. Guys, wait until chapter 5 when we're talking about routing. Then you will understand a little more what August and I are talking about. Okay? But essentially, August is trying to point out that even though IP address is designed in this conveniently hierarchical way, seemingly efficient, but in practice, in BGP, the internet routing, it's not working exactly what the original designer of IP address space was hoping for. Okay, now let's go on and show you the third video. Okay, so you see that one can actually allocate the IP addresses in this hierarchical way from bigger net to smaller net to smaller net. Okay, something nice about hierarchical addressing and prefix matching is this: if you move one of the smaller net, okay, away, it's actually not necessary to reassign the IP addresses with the longest prefix match for forwarding. So here's the video to show the case.
So the slide here is actually introducing a very interesting scenario. Okay, organization 1 originally here is moved down here to a different ISP. So that prefix advertisement will travel down this way, and ISPRS will try to aggregate it with the original IP address block. Well, ISPRS will find that unfortunately the two of them are not aggregatable. In this case, two separate advertisements will go on out into the internet. The forwarding table here will contain two entries. One is starting with 199 and one starts 200.something.something 18.0 and 23 bits. This one is 16 bits. And of course, this entry here, okay, will arrive also at the router here at the internet, on the internet. And therefore you have 200.something, 16, and 20 here. So this entry is going to take the packet out this interface. These two entries is going to take packet out here. So if there is a packet coming in that is supposed to go to organization 0, it's going to match the first entry, isn't it? Okay. It's not going to match the entry number 3 because, hey, this address space and this address space, they are actually disjoint. Okay? So not going to match this guy here. So packet going for destination organization 0 is going to go down and travel and down to organization 0. So setting up the forwarding table this way, not a problem. Similarly for organization 2 and 3 and all the way to 7. Okay? As long as the destination IP address is matching this, it's going to come down this way. Yeah, I know you're thinking, hey, what if the packet is going for organization 1? You're right, it's going to match the first entry. Ooh, a bit worrisome, yes. But if you look down the table, right, hey, it's going to also match entry number 3. Now, if we call back in section 4.2, what did we say? We're actually not just doing prefix matching. We are doing what? Longest prefix match. So which one is the longer prefix? 20 versus 23. So packet carrying destination for organization 1's machine is going to come down this way here and eventually reaching organization 1. So we're okay, right? So the overhead of sending the advertisements is still very low. Now slightly higher here if it's not exactly aggregatable, but forwarding is going to be fine. And we allow what? Organizations moving from one ISP to another ISP without changing the physical IP addresses. Okay? Therefore, all these servers are running here. They can stay using the same IP address without needing to change the name to IP address mapping. Now, we get the block of IP addresses from our ISP, but next question to ask. How does the ISP get its own block of IP addresses? So it's like saying, hey, the system admin asks the higher level system admin, but higher level system admin asks the even higher level system admin, right? And this goes on. Who's the highest level system admin? Where's the end? Yeah, this organization is the end. So ICANN here is the highest level system admin. This is a non-profit organization overlooking, okay, the allocation of the IP addresses, the allocations of the domain names, and managing also the domain name servers. So very important organization. We normally don't know. Okay, only the people who knows about the internet knows a little bit about ICANN.
All right, so that was hierarchical addressing, hierarchical routing. From that scenario you saw in the video, you can also see what August was talking about. If we move organization 1 down to another ISP, it will work, but it's not as efficient. If we just move it down here without changing the IP address such that it matches the new ISP's prefix, then this new ISP will need to advertise 2 entries. So you see that the forwarding table at the big router there will now have 3 entries. If organization 1 changes the IP address such that it's within the prefix of the new ISP, then you have only 2 entries here in the big router. So, convenience versus efficiency. Or what I said here is policy versus efficiency, because policy is often set by people, and people are always going for easier solution, okay, a lower labor cost. Okay, in this case, reassigning the IP addresses might create a lot of operational bugs right after the change. Okay, so you see, yeah, convenience, stability, okay, versus efficiency. Now, we go on to the second set of topics today. Okay, NAT and IPv6. Okay, so these 2 topics are all about addressing this issue, a very serious issue, IP address space shortage problem. We don't have enough IP addresses. All right. So let's check out the first solution called NAT, Network Address Translation. The idea is this, yeah, so we don't have that many IP addresses anymore. How about a bunch of the machines share one real IP address? Okay. Now, for these machines to configure, they will use fake IP addresses, and there's some sort of mechanism here, okay, at the box, okay, coming out of these machines, such that it translates from the fake IP addresses to the real IP addresses that are shared. And of course, vice versa, from real IP address somehow back to these machines as fake IP addresses. Okay, so that's the general idea.
NAT, the Network Address Translation Service. This is one of the most used protocols on the internet these days. It's here to address a very serious problem. We're running out of IP address space. Yeah, 2 to the power of 32, it sounds like a high number, but we do have a lot more hosts, a lot more router with network interfaces requiring these IP addresses. Therefore, IP addresses is a scarce resource on the internet. To get one, you pay quite a bit of money. This is also why, okay, if this is home network here behind the local network, your deal with the ISP is often this: you pay a specific amount of money monthly, you get a certain downlink bandwidth, certain uplink bandwidth, and a certain number of IP addresses. Usually you get 1 static IP address or 4 dynamic ones. Okay, if you pay more, maybe 8 dynamic ones. But essentially, the more IP addresses you need being allocated from the ISP, the more money you pay. So it's not like every family can afford paying that much. So to try to save money, this is what we often do at home. Okay, we just subscribe for 1 IP address, and then we create a home network. Okay, using some fake IP addresses that we make up, and subnet address that we make up. So instead of asking the ISP, okay, asking the system admin for a block of IP addresses, we can afford it. We use fake, okay, block of IP addresses. So we call this local network or home network. Each of the machine, each of the interface is assigned an IP address on the fake subnet. Okay, so these are then fake IP addresses. Now, as long as we're sending data within ourselves, should be fine. But if we want to send data out, wow, we need to be careful. And that's when we need a NAT server here at the home gateway. So NAT is sitting right here. So all packets that's leaving the local network needs to be using the real IP address, the IP address assigned by the ISP. Otherwise, it's going to be dropped, okay, at the ISP. So now if this guy has a connection to go out, and this guy has a connection to go out, and this guy has a connection to go out, yeah, each of these connections to not collide to each other will be assigned a new port number as well here, okay? A different source port number. Source IP address changed to the global IP, the real IP, and the port number changed to a different number so that they don't collide to each other. So that is the general idea of an AT. We'll describe the detailed mechanism slightly later. What's nice about NAT is this: we don't need to ask the ISP for a block of IP addresses, which is very expensive. One is enough, save us lots of money. There are 3 more benefits, in fact, using NAT. One is this: if we want to change the IP address in the local network, we just change it. It's not like, we're changing the IP addresses of the gateway there, which is a global ISP, which is assigned by the ISP. Then we need to inform the ISP we're changing it to somewhere else. Otherwise, traffic is not going to flow through. Okay? But if we're just changing the local machine, then there's no need of informing the ISP. Nice, convenient, so save us time. Third benefit, well, if the ISP is not providing good enough service, we can actually switch to different ISP. And the IP addresses we have on the local machines, we don't have to reconfigure them. We just stay using the same fake subnet address, fake IP addresses. The last benefit is slightly unexpected to many of you. Okay? Those devices inside the local network, those 10.0.0.1, 10.0.0.2, those IP addresses are fake ones. Packets originated from outside, from the internet, carrying destination 10.0.0.1 is not going to flow through the internet and reaching the gateway and therefore coming back to the host. Because the IP address of the gateway is what? 138 something. That's the real IP address. That is also what people call the global IP address. And that fake address there is the virtual address, the subnet address. Okay? So subnet or virtual address or fake IP addresses are not addressable. By not addressable is, what I meant is packets coming from originated from outside just have no way of reaching. Okay? So they are therefore not visible from the internet, not visible from hackers in the internet. So it's a security plus, okay, unexpectedly.
Okay, so the benefits of using NAT, really nice, cheaper, right? There's no need to do much if we change on the device end or the ISP end. And finally, hey, it's somehow more secure as well for the devices behind the NAT box. Now, next video, let me show you exactly how it works. 3 steps. Okay, and right after I describe the 3 steps, I'm going to show you an example.
NAT's mechanism is quite straightforward. Only 3 steps. 1, 2, and 3. Step number 1, you heard about it a bit already. So this is to handle when packet is going out from the local net to the world. We'll have to replace the fake IP address with the real one. We'll also replace the source port number with a new port number. Okay, so the source IP address, the source port number, these 2 fields are replaced with these 2 values. And this pair, so 1, 2, 3, 4, okay, are also tracked, okay, being remembered in NAT's translation table. So the source IP and the source port number, as well as the translated source IP, source port number, will be maintained as a pair in the translation table. So when the remote hosts receiving this packet and sends back a response, in the destination IP address, it's going to be the real IP address, and it's going to be the new port number. So that packet's coming into the local net. The net box there is going to look up the table and find the pair, right? So it's matching this IP address and matching this new port number, and therefore translate the IP address back to the corresponding port source IP address, and translate the port number to the corresponding original source port number. And therefore, you see the destination fields is going to be replaced by the original IP and the original port number. And that packet then will travel the local network and reaching the destination. Let's use some animation to illustrate. It will be easier to understand. So the local net here, using a fake subnet address. So this machine here, 10.0.0.1, is sending a packet to a web server, okay, outside of the local network, okay, inside the internet. The packet is going to look like this. Source IP being the fake IP. Source port number being the port the web browser is sitting on. Destination IP, the server's IP. Port number, the web server's port number. So that packet is going to reach the net box in the middle, and this is going to be replaced. This is going to be replaced. So 10.0.0.1 is going to be replaced by the real IP. And the 3345 port number is going to be replaced by a new port number generated by the net box here. Step 2, the net router there is going to add an entry into the translation table so that we know this old IP, this old port number is now being changed to this new IP and this new port number. When this packet reaches the web server sends back a response. Destination address will be the source of the request. Okay. So destination port, yeah, the source port number of the request. Now this packet will come back to the net box in the middle, and one more translation is going to be done. So this time, the process exactly is this. Let's look at the destination port number, and then go to the table. Look up the entry in the table such that the port number in the WAN part matches the destination port number. Now, destination IP address is definitely going to match the WAN side of IP address because the WAN side IP address is going to be just 138.76.29.7. So this unique new port number is the key. So destination port number, you look up this value in the translation table. Identify the entry, and then replace the destination IP address with the LAN side address. Okay, port number also with the LAN side port number. And that's why we see destination IP address, now the fake IP. Port number, now the original browser's port number. That's how net works.
All right, so rather straightforward. The last video, so we've talked about all these benefits of using NAT, but there are some issues as well. Yeah, that's what this video is about.
Last are the drawbacks of NAT. Point number 1, port number, pretty short, 16 bits only. That is also saying we could have only up to 60,000 simultaneous connections. If the local network there is for home use, this is plenty. But if the local network there is for enterprise use, if a company is there trying to save money and subscribing to only one real IP address, having lots of employees, lots of machines inside, chances high the packets going for one flow might be mistaken, okay, with the other flows. Point number 2, NAT is controversial. In the previous slides, you might see the authors of the textbook referring to these NAT devices as NAT routers. But routers are what? These devices in the core of the internet. Now, routers implement only 3 layers of protocol: physical, link layer, and network layer. So routers are also called the layer 3 protocols. Now, layer 3 protocol is supposedly only accessing layer 3 packet header. Layer 2 protocol accessing layer 2 packet header. NAT, if you think about the mechanism again, it's what? Replacing the IP address fields in the packet header. It's also replacing port number, the port number fields in the packet header. IP address, that is a field in the, layer 3 packet header. We learned about the IP packet format already. But port number, if you recall, in chapter 3, the transport layer, port numbers are there to differentiate different processes running on the host. It's actually a layer 4 notion. It's in the transport layer header, in the layer 4 header. So NAT as a router should not be doing that. So those who are against NAT boxes to address the network shortage, IP address shortage problem, argue that we should probably, improve IPv4 such that we have more bits for the IP address field. So IPv6 is the next generation. It's using 128 bits for the IP address, much longer. We'll talk about this later. Point number 3, NetBox. Hosts sitting behind NetBox cannot be reached from a machine from outside. So that was actually presented as a benefit, a security benefit earlier, right? Hackers cannot be sending packets to 10.0.0.1 because that packet is just not going to go anywhere. Not even reaching the NetBox in the middle, the IP address being 138. Something. Right? Only packets with the destination address 138. Something will be able to reach netbox. Okay? And netbox there, it will also not know, right? What port number, what local IP address to convert back to reach 10.0.0.1. So yeah, it's actually hard to reach local hosts from outside. So if packets are originated from outside, that's not going to work. Packets originated from inside, however, works. Now we know, right? So from 10.0.0.1, need box tracks the local IP address. Okay, keep it in a table. That packet gets translated using global IP, using real IP, goes out. Packet will come back to the router, and the netbox look up the table and then translate back. So originated from inside, no problem. But data originated from outside, big problem. And this is a serious problem for these designers, P2P protocol designers. In P2P protocol, a lot of time we will try to establish connections between one user's host to another user's host. You and me being hosts, we are, chances high, sitting behind the net box, sitting behind the net router. So we'll have trouble calling directly to each other, setting connection directly to each other. If you recall in Skype's protocol design, making a call, the designer of Skype actually take extra step. Okay? Bob and Alice will need to call a relay peer, and the relay peer will exchange packets for each other. Okay, for these two peers, for Alice and Bob. So, application layer designer now need to worry, okay, in case layer 3 or layer 4 protocol is going to break. Okay, unexpected might happen. So, one layer's protocol designer needs to worry about another layer's, how it's designed, how it works. That's breaking the end-to-end argument. So by this here, okay, what I'm saying is this. The reference protocol stack there, okay, application, transport, network layer. So we say nice about, building the network protocols and separate them by layers so that it's modular. Designer in one layer does not need to care about, what's inside another layer. Exactly the same thing we are arguing here. Application layer protocol needs to worry about another layer's protocol, how it works. So that breaks the modularity there we have in the original reference stack. And that is what end-to-end argument is referring to.
All right, so those are the drawbacks. Okay, but as you can see, 2 out of the 3 issues are more philosophical. That is why NAT is very popular these days, because the benefits seem to outweigh the disadvantages. Okay, now let's go on to quiz 37, ideal versus practical. Okay, are you more an ideal person, or are you a person who always look for practical solution? Okay, so to speak. Q1, so this is like a test to see which type you are. So Q1 asks, would you prefer paying for multiple IP addresses or using NAT? Okay, then you pay only for one IP address. I know it's subjective, you take your pick, but tell us why. Okay. Q2, would you prefer using NAT or the alternative IPv6, which is a way bigger address space? Okay. Again, subjective, but tell us why. Okay. Let's move to the score. Channel W12, quiz 37. Guys, you have only 4 minutes this time. Okay. After 4 minutes, type up your solution in 1 minute. Okay, August. Okay, this, no NAT, period. I feel that you feel really, really strong about NAT. So, ideal person, August. Yuji. Practical, maybe you are more? Let us know. Okay. And August, I guess you can afford more. isn't it? But I can understand also that people in certain professions, end-to-end connectivity is a must. Yeah. Oh, wow, 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 wow. Yeah, I think chance is very high that August you are hosting servers. Yeah, it is. It is. It is. Lucas, representing team 2. I prefer NAT. Okay, Lucas, you sound like a student. Yeah, you sound like a student. It's just more practical. Practical, definitely, Lucas. Think your teammate is Matthew. Matthew, are you ideal or practical? IPv6. Okay, I'm a little bit torn. Lucas, you are practical, answering Q1, but ideal, answering Q2. How about IPv6 and NAT? I don't know. The number of devices we have and we put connected to the internet is exploding. Don't you think so? Maybe one day IPv6 and on top of that we are still using NAT. Matthew, practical. Okay, we are the same type. Okay, let's see. Dual stack is the way to go. I mean, hey, my machines are dual stack. Many of the NTU machines are dual stacks. The routers, at least I know, are IPv6 capable. I think more the business sectors are more often we see v4 only cluster, and maybe developing countries. So I'm always curious about how the internet is like in developing regions. Okay, that's something related to net neutrality, which I feel very, very important and very, very important issue. So in a world where the economy is not going all that well, fairness is very important. Okay, so I see the other groups are converging to some answers. Team 4, Ali. Q1, cheaper and more secure. I guess you're choosing one NAT, right? One IP and then NAT. Q2, IPv6 because it's 128 bits. Limitless number of IP addresses for now. Okay, I see. Effectively removing the knee. Okay, good. Yeah, so I think Ali, very practical. You are a very practical person because you're thinking that with IPv6, there's no need of NAT, okay, and you get the same thing. So as practical as your answer for Q1. Okay, NAT can pay more. I'm sensing that for the rest of the teams, Q1 will be NAT, Q2 will be IPv6. Yeah. Interesting. Shorter delay, bigger throughput. How do you know? Have you studied IPv6 already? Yeah, in IPv6, packet forwarding will be faster indeed. Team 10, using NAT because it avoids NAT issues. Very interesting. Yeah, so Boyao is also very practical because you don't need a real IP, not hosting servers, for example. Not running the P2P applications, for example. Very interesting solution. IPv6 because you're looking long term. Team 5, prefer paying only one. Yeah. Make use of IPv6. NAT? Okay. Yeah. Team 7, brave. You don't mind being different. I like that. I like that a lot. Using NAT and using NAT. All right, so Team 17. Oh, you like NAT. Not because it's cheaper, because it's more secure. You know, I have to agree, Tasha. Security, more important than money. Okay, to many of us now. Okay, can totally agree. So you choose NAT, but the reason is not quite the same as the others. Useful for the future. Doesn't necessarily give you higher performance because NAT is gone. Yeah, so by the way, packets going through the NAT box, even though the translation seems easy, there's still a table lookup service, right? There's a translation table. That's going to take some time. Okay. Yeah, thank you, August, for adding to what I have commented on. Team 4 saying that IPv4 is going to be faster. Yeah, I guess if you use IPv4, then you don't need the netbox. Without the netbox, it is faster also, right? So that's what August is trying to say, isn't it? And NAT, you pay less? I don't like 128-bit address. I see. Intuition, you think. As I said, subjective, your choice. It is long, okay? Later you'll see, Yuting, your intuition is actually right on, because 128 bits versus 32 bits, that's 4 times more bits. The packet header is actually longer. IPv6 packet header longer than IPv4. Clara? Clara. Struggling. Lots of expression here. Yeah, I know. You and your teammates, very interesting couple there. Clara says 2. So you prefer NAT. Heather, don't mind paying more. Yeah. And Heather is actually thinking for the public good, right? Clara says 16 bits. You know, Heather, you two are just the opposite of each other. You know what? Having teammates opposite of you is a great thing because you complement each other very well. You always see another side of things. That makes your team solution more robust usually. Okay, too many. Too less, too many. Ouch. Oh, by the way, Clara, it's 32 bits. Okay. IPv4, I think 32 bits, right? 13. Cheaper, more practical. Future trend. Yeah, interesting. Yongyi is going with the flow because people are moving to IPv6. Yeah, going with the flow will be easier. NAT, cost effective and secure. Both reasons. Yanjia. Very good. Wait until the last to say. Hey, the benefit is that you give the full reason. IPv6. Yeah, so IPv4 is gradually, going off the stage. It was the center of the stage of the internet. It is gradually going off stage, and eventually we'll see just IPv6. Length also depends. For example, below addresses both belong to the same box. I see what you're saying. Yeah, so this is I think address in terms of characters, but when it's converted back to the network byte, then IPv6 is still going to be longer. Yeah, because in IPv6 we now use A, B, C, D. Each digit, the range of the values is bigger. Okay. Team 8. Again, wait, last but not the least. Okay, using NAT and NAT. Yeah, very practical choices, Team 8. Very, very practical, Su Chen. Yeah. All right, so NAT. Now let's check out IPv6. How about that? Okay, so the first video is just to motivate IPv6. We thought that the address space is the only motivation, but no, not quite. There are two more motivations.
Last topic in 4.3, the IPv6. This is also the protocol some of these network engineers thought more legit, addressing the IP address shortage problem, instead of using these controversial netboxes. And that is why we actually upgrade from version 4 to version 6. The approach is very straightforward, expanding the 32-bit IP address space to 128 bits long. So the main goal of having IPv6 is exactly this. There are two secondary goals. First is to speed up the processing or forwarding of the packets as they come into a router. So in the data plane, packets coming in really, really fast. If we could reduce the forwarding time, processing time, we made the transmission process as efficient as possible. So you'll see in IPv6, the header is also changed to try to reduce the forwarding time, the processing time. The secondary purpose, this. We want to add something so that we could label the packets, so we could separate a group of packets from other, and make them flows, different flows. Now, with the different flows of these packets, we could then assign priority to a specific flow versus lower priority for other flows. Therefore, we could establish a more flexible levels of quality of service for these different flows. You see also header fields there to support labeling of flows, setting priority of the flows.
Yeah, so you see, allowing priority, and what was the other one? Okay, probably forgot. But hey, you get the idea. Expanding the address space is not the only reason to have IPv6. All right. Second video now is a little bit long, 7.5 minutes. You will see Polly talking about the size of the IPv6 packet header versus IPv4, and then introducing formally the IPv6 packet header. Okay, so in terms of size, IPv6 is bigger still than IPv4, but the benefit of IPv6 is something you will see in the IPv6 packet header format. It's a lot more compact. You have only very few fields. Okay, so pay attention. This is an important video.
The IPv6 packet format. The header part of it is fixed size and 40 bytes long. Now recall version 4. Is it fixed size or variable size? It's actually variable size because of the option fields there. So that field, in case we have more options, then it's going to go longer. No fields, 0. And therefore, IPv4 header size is 20 bytes minimum and could potentially be more. Now you probably recall, right? When we were talking about the IP header size, 20 bytes, we also mentioned the TCP header, 20 more bytes. Together, 40 bytes, just to store the control information. If we're sending a real message that's 10 bytes long, the entire packet will be this long, while only 10 of them is effectively sending data. This is very low utilization. So yeah, Polly kind of promised you that in the next version of IP, we're going to reduce the size of the header. But you see here, is 40 longer or 20? Yeah. 46 in fact has a longer header. But this is necessary, and this is as small, as short as possible already. Allow me to explain. In the IP packet header, there are two fields called the source IP and the destination IP. In version 4, the IP address space is only 4 bytes long. Now, to store source and destination IP, you only need 8 bytes. But in version 6, the main goal is to expand the IP address space. So unavoidably, we have very long IP address, and two of them, one for source IPs, another one for the destination IP, together 32 bytes. If you look at this, version 6 header 40 bytes, so we have only 8 bytes for the additional fields. While in version 4, 20 bytes long, we have 12 bytes for the additional fields. So the designer of IPv6, you see, try very hard to reduce these other unnecessary part of the header, removing them away, removing these fields away from the header. Okay. So 40 here, longer indeed, but it is actually after we try very hard making the header part as compact as possible, as small as possible. In fact, the second feature of the version 4 header is this. To recall, in the fragmentation and reassembly function of IPv6, we have these 3 fields in a row: ID, fragmentation flag, and offset. This row of extra header fields remove entirely, okay? And this is done by disabling the fragmentation and reassembly function in version 4. So in IPv6, no longer allowing fragmentation. And this is why we see the version 4 header, although longer, it looks really clean and compact. Okay. First, the source address. Second, destination address. And the rest is only just 6 more. 1, 2, 3, 4, 5, 6. First, here is the payload length. If you recall in version 4, we do have what? The header length and the entire packet length. Because the header size can vary. And the packet size, because the data size can also be different, so we need 2 lengths. Here now, having a fixed packet header size, we need just the payload part, okay, the payload length to indicate the size of the data down here. Hop limit, this is just the TTL field, okay, just like in IPv4. Next header, it looks odd, we've never seen this before, but this is really the upper layer field in version 4. So what it does is, once we extract the payload, we actually forward the payload to what's indicated by this pointer here. And so further processing will be done using this handler on the payload. The version field, we also have this in version 4. So the only difference is that this value will always be 6 in version 6. Priority and flow label, these two are new. So flow label here is to allowing us to group a specific set of packets together. Okay, so coming from one application, coming from one service, they could be carrying flow ID 1, and other packets from other services, flow ID 2. So we could identify packets for one flow, okay, and packets for yet another flow. So we could separate these packets, troubling the internet. As a result, we could then provide different priorities to different flows. So some flows will go earlier than the others. Therefore, we provide flexible levels of these QoS. Now, there are some more fields we remove, okay, not just the fragmentation fields. The header checksum in IPv4 header, that is removed because to calculate checksum takes time. To check the checksum takes also time. So let's try to reduce the forwarding processing time as much as we can. So let's remove the checksum part. And take the risk of some bits in the header being flipped. We might have some, might run into some errors, but chance is very low. Okay. We way higher here, way more here, trying to make sure the forwarding part is fast. And we move the option part down to the payload, so that when we grab the payload and give it to the handler is going to look at the first few lines in the payload, and those will contain the options. Okay. There's one more thing. ICMP version 6. What is ICMP? You need to think back. In one of the earlier overview slides, I was talking about the functions and protocols implemented in the network layer, right? In the data plane, we have forwarding. In the control plane, we have routing and management. ICMP is one of these protocols implementing the management function. Okay. So we also extend the version for ICMP to version 6. Okay. And the reason we need the version 6 ICMP is so that we could send a special message, packet too big. Okay. Allow me to elaborate. Now we don't have fragmentation and reassembly, but the fact that some of the links on the internet allows smaller MTU is still there. So what if we have big datagram coming to a router and the next link is saying MTU smaller, but we cannot fragment this datagram anymore? What should the router do? What can the router do? Okay, so the mechanism in version 6 is to send a special message, an ICMP version 6 message, back to the data source saying packet too big and the better packet size is below this MTU value. Okay, so there's additional message being defined in ICMP version 6, allowing the routers to manage themselves, deciding what is the best datagram size. And we'll just ignore this part. Multicast, we'll just not talk about it at all. Okay, it's a can of worms. So this is IPv6 packet format.
All right. So there's another video called tunneling. It's a technique used for us to bridge IPv6 clouds to send data over a IPv4 network, right? As we were talking about, whether you would prefer moving to IPv6 or staying IPv4 and using NAT. Many of you says, let's go IPv6. So we are going to IPv6, but it's not something that we can change one day, okay, overnight. Okay, so we are moving gradually from IPv4 to IPv6. So what happened is that the part of the internet is IPv6 part, IPv6, but there could be a big cluster in the middle that is still IPv4. So to send data across IPv4, we try to set up a tunnel, okay, across the two IPv6 clouds so we could send packets through. So that video is a little bit long, about 6 minutes. We'll not play that in the lecture. So guys, if you're interested, go to the video list and look it up and watch that. And so I'll just play the last video called IPv6 adoption rate.
Last slide here is not technical at all. It's to talk about the adoption of version 6. So Google once released this number. 8% of the clients worldwide accessing Google services are IPv6. Pretty low. NIST is a government body there tracking all sorts of standards as well as maintaining some statistics. So NIST releases this. 33% of the US government internet is IPv6. Okay. US government is promoting strongly the move to IPv6. And to make the numbers even more pathetic, this is after 20 years of effort. Ouch. But why, right? If you think at the application layer, we have new applications rising. Okay, IG, Facebook, Netflix, other video streamings. Okay, Zoom, YouTube. Okay, newer services rising. Within each service, the protocol also get upgraded quickly, right? Changing from one version to another version. But unlike application layer changes, network layer changes, it seems very hard to do. It's not like undoable, right? We just need to upgrade the routers, upgrade the clients, reconfigure the routers, reconfigure the clients. Why is it so hard? Why is it so much easier to upgrade one app?
Okay, why? Well, hey, you guys can try to figure out. If you think that there's a good reason that it's hard to move, let me know. But August was right. 8% climb being IPv6, that was decades ago. Okay, nowadays, I think as of May 5th, I think just a few days ago, IPv6 is about 44.55%. Okay, if you look at the box on the upper right, that is the Google latest statistics about IPv6. Okay, so yes, August. Yeah, almost 50%. You're correct. Okay, 44.55. to be exact. Good. And you know what? That's all the time we have today. And guys, I'll see you next week. Okay, goodbye. Bye. Go get lunch. All right. There you are. Bye-bye. Okay, bye. Bye, Yongyi. Bye, Lucas. Debate. 16. 13. 15. Boyer gets a toothbrush from the teammate. Okay. What I wonder what that means. You guys are funny. Alright, Ming Hong gets a support from teammate. Let's see. From Cassandra. Very good. Team are you? Alright, 11. Zhixiang, team 10. Zhixiang, team 12. Team 9. Ali is team 4. Missing team 6. Maybe we're missing team 6. Yeah, Lucian is not yet here. But I think. Alright, guys, that's all.